All right, so today we're going to start chapter 4, and we're going to turn our attention from derivatives to antiderivatives. But what I'd like you to do first, on the front page of your notes, which it looks like about half of you have printed and half of you haven't, is that you're going to just write down the derivative rules that you know and love and have been working with now for, 6-8 weeks, something like that, okay? So we have these 5, so jot those down, especially if you don't have your paper with you. And then I'll flip the screen and you can jot down the rest of them. For those of you who have the printout, you've got all of them already there for you. So we have the constant rule, the linear function rule, our constant multiplier rule, sum difference, and power. So write those down and then I'll flip the screen and we'll show you the other, there's 6, it's the trig rules that are left. Once you have them written down, you can start working on just writing in the derivative that you know that goes with it. Okay, the trig rules were these. They're all of our 6 trig functions. I'll flip back to the other screen in just a second, too. All right, so we're going to write down the derivatives for each one of these. If you've got your printout, you've had time to do that. What is the derivative of a constant? It is 0. So the first one should be y prime equals 0. What about a linear function, right? Like y equal ax plus b. What's the derivative? It's just a, right? The slope of the equation is constant, so that is my tangent line's value, right, or the derivative's value. How about when I have a constant multiplier? What's the derivative of k times f of x? I have the k that comes along for the ride, and then I have my f prime of x. What about sums and differences? Right, so we just take the derivative of each of them independently, right? And then we add or subtract them together, however they were compiled to begin with. How about the power rule? In x to the n minus 1. Yeah? Good deal. Okay, so those were ones we did like the very first day of 2.2 was where that section came from. These others showed up across a couple of sections. The first couple of them showed up in 2.2, and the next one showed up, I think it's in 2.3. What is the derivative of sine? Cosine. How about the derivative of cosine? Negative sine. Those two are the ones that we tend to remember the most easily. The others showed up a little bit after that. What's the derivative of tangent? Good. The secant squared. And how about the derivative of secant? Secant x, tangent x. How about cotangent? And cosecant? Okay, that's all review. We've done it all many a time at this point. But what we're going to do is we're going to take the things that we have on the right-hand side, for instance on this screen, or even on the right-hand side back on this screen, and we're going to go backwards. Okay? That's what antiderivatives are. So it's very much like when you learn division. Okay, I have a child in my house who's learning multiplication right now, and I know what's coming next is division, right? If she learns her multiplication facts really well, she should be able to go back into division pretty easily because it's an inverse operation. The same thing's happening when we do antiderivatives. If we know our derivative facts pretty well, we should be able to go back into it, backwards with antiderivatives pretty easily. So we have antiderivative rules next. We need a little bit of notation. The reason we need some notation in particular is because you'll notice the functions still say y equals, right? And they don't start out saying y prime. They could, but these are not the way that they're written to start with. So what we do when we write a antiderivative, since I don't have just like a prime to take away, is that I capitalize it. So there's going to be capital Y's on all of our antiderivative pieces. Okay, so that's one thing to remember is that I'm going to capitalize things. The second thing that I have to remember is that when I take the derivative of constants over here, what happens? It becomes 0. So in a very real sense, this plus b, for example, when I take the derivative of y equal ax plus b, could have been anything, right? And the derivative is still a. So this plus b at the end, it can fluctuate, it can vary, and I don't get a for sure, like what's really did it come from? Because there could have been a plus or minus something at the end that just disappeared. So on antiderivatives, every time we take an antiderivative, we have to put plus c at the end. Because really what we're doing when we're finding derivatives is we're finding slopes, right? Well, the slope is not contingent upon whether the graph is, say, like right here on the graph or right here on the graph, is it? I can shift it up and down and not change the slope at all. And that's what the plus c on the end is going to indicate to us, is that I have the ability for it to be located at a different point in space and the slopes to still remain the same. So, keeping that in mind, how did we get a derivative that was 0? What did we take a derivative? What did we take a derivative of? Not a variable, a constant, actually. So over here, when I got the derivative as 0, it happened because I was taking a function that was constant to start with. So over here, when I go backwards, and I just had 0, I would just get a constant, and we're going to use c for all of our constants. Don't forget your plus c's. I'm about to do some more. They're going to show up everywhere. On the next one, the slope is a constant now. So over here, when I had the slope was a constant, this is the second line. Where did I start? Well, I had a line, right? I had a line, and that's how I got a slope that was constant. So over here, if I'm starting with a derivative that is constant, a function that is constant, and I'm wanting to go backwards, I need to create a line out of it. So that k will now be the slope, so it's kx. And then I potentially have a plus c at the end to shift it up and down. So instead of taking away an x, I insert an x, right? Instead of turning something into 0, I put something back in that would then become a 0 if I took its derivative. Everything is backwards. Now, the interesting thing that happens with constant multipliers and some difference rules is that I apply them in exactly the same fashion. So just like the constant multiplier, the constant just came along for the ride. When I go backwards, it comes along for the ride as well. It just continues on, and so the k is going to stay the same. And then I take the antiderivative of the other piece. So this is the capital F of x. And then I put a plus c. Sums and differences, they function the same way. We take the antiderivative of each piece. So I have the f of x, and I have the g of x capitalized for antiderivatives, the plus or minus in between, and then what goes on the end? Plus c. So let me just pause and make a comment right now that when you get to the gateway, what's going to be at the end of every problem that you're going to do? Plus C. It's been a number of years ago, but one time I had a guy, he got everything right. Every single problem was right. He would have had a 20 out of 20, except he missed plus C on every single problem. And I didn't give him the credit. It's really harsh, I know. Those plus C's really matter. So I don't think he forgot a plus C ever again, probably in his entire life, okay? All right, so plus C's. The next one, this one's the most interesting to go backwards. Okay, so let's think about what we did with the power rule. With the power rule, the exponent, became the coefficient, right? And then we decreased the exponent by 1, okay? Now, becoming the coefficient means I'm multiplying by that n now, right? So the effect is I multiplied by the previous power, right? And I changed the power to be 1 less. So we're going to take this in pieces. Instead of making the power 1 less, what would be the inverse of that? Add 1. We make it 1 more. So instead of the exponent being n, it's now n plus 1. And instead of multiplying by something, we are going to divide by something. And in particular, in the previous time, I multiplied by the previous exponent, right? What I had before the n. Now I will divide by the new exponent. And if you're in doubt, take a look at what would happen if I took the derivative. I need a plus C, but that aside. If I took the derivative of this, well, if I took the derivative of this, n plus 1 would come down to the front and cancel with the n plus 1 in the denominator, right? And the exponent would decrease, going from n plus 1 back to n. And I would get back exactly to this piece right here, right? Yeah. All right, so these last ones, the trig ones, what you'll notice is that with the exception of the negatives, they're exactly the list that shows up on the right-hand side here, aren't they? With the exception of the negatives, it's exactly the same list. That's important to realize because right now what we're saying is that in this section, there is no derivative of cotangent. I'm sorry, antiderivative of cotangent. There's no antiderivative of cosecant, right? It's only cotangent squared. I'm sorry, not even cotangent squared, cosecant cotangent and cosecant squared. So you might be saying, well, what about those other ones? We'll get to them. It's just not in this section. Okay, this section is really just taking everything in reverse. So if I take sine, whose derivative was sine? Cosine. And I need to be careful. Was it cosine's derivative is sine or cosine's derivative is negative sine? Negative sine. So I have to put the negative on here. The derivative of cosine is negative sine, and it says positive sine here. So in order for that to happen, I would have had to have started with a negative cosine. And I have plus C. Whose derivative is cosine? Sine. And that one is positive, yes? Whose derivative is secant squared? Tangent. And whose derivative is secant tangent? Secant. Okay, so far so good? These last two, if you look back at your list, the cosecant squared and the cosecant cotangent, they're negative on your list right here at the bottom. Yes? And they're going to be positive on the left-hand side here. So in order to get them to become positive, the corresponding pieces must be negative to begin with. So whose derivative is cosecant squared? Cotangent. And the sign has to switch, so it's negative cotangent. And whose derivative is cosecant cotangent? Cosecant, right? Yeah, cosecant. And again, the sign switches, so I need the negative to represent that I'm going to switch the sign when I take the derivative, to take the antiderivative. Okay, 2 pages of things, right? The only page that's new is the second page that we just did, the second list of problems. And what we're going to do now is just examples that do this. Okay, there's a caveat to the ending examples we do, but the first ones are going to look and feel exactly like what's going to show up in your gateway. All right, so you're going to have problems that look something like this. The notation will look a little bit different from problem to problem. This is one of the notations. All right, so this S thing in the beginning looks like this like narrow, skinny little S means antiderivative, okay? You can also say it means integral. The phrase antiderivative and integral are used interchangeably. And we'll talk more about both of them and kind of when you see them used. But they mean the same thing in terms of operational status. So I will tell you that I'm not real careful. I will use them interchangeably because they are going to mean the same thing for us. So if I say integral or if I say antiderivative, it means the same thing. All right, so what happens is it's very much like these are bookends. There's a script S at the beginning and there's a dx at the end, kind of like putting a parenthesis at the beginning, a parenthesis at the end. They're either both present or they go away at the same time, okay? So once I eliminate and I take the antiderivative, both the bookend on the front and the bookend on the back are going to go away. That's important to realize. What in the world does the dx at the end mean then? Well, the script S at the beginning means take the antiderivative. The dx at the end is telling you with respect to what variable. And you might be saying, well, there's only one variable. And you're right, there is, but there won't be forever. Now, for some of you, there will be forever because you're not going to go far enough in calculus that you'll ever see this happen. But the reality is that eventually, when you get to calculus 4, which some of you will get to, you will have functions of more than one variable. It's called multivariable calculus. And so in order for that to ever work, we need notation that specifies the variable. So that's why it's showing up. It's showing up for the extensions to further dimensions of calculus. Fair enough? Okay, so the dx at the end is just specifying the variable of the function. So we're using the variable x for this one. So we're starting with 2x. All right, so 2x. I would write down the 2 because it's a constant multiplier. X's power right now is a 1. So I need to increase the power by 1, so the new power will be a 2. And I divide by the new power, 2. It's not the only way to think about it, but it works pretty well from the ones we've experienced. The next one, I have a 3, comes along for the ride. The power is currently 2. So if I increase the power, it will become 3. And I divide by the new power, 3. And what do I need at the end of the problem? Plus c. Now you might be saying, why didn't we just take the 2 that's at the beginning and drag it up, or take the 3 that's at the beginning and drag it up? You could, but it's not always a 2 that becomes the x squared, right? There could have been another number there. So a more general idea is what I just did right here. So for the purposes of the gateway, this is what you would leave your answer as. Remember, no simplifying on gateways? This is the answer. But let's be real. If you write 2x squared over 2 and you don't cancel out those 2's, we're missing some algebra, sort of like we should be able to do that. That's not a big deal. So we're going to simplify all of our values and so forth when we do anything on quizzes, on exams. WebAssign's kind of finicky. Sometimes it will let you not simplify and sometimes it wants you to. So whatever it does is whatever it does. But for the things that you turn in written form, we'll simplify this. This 2 and this 2, this 3 and this 3, they're going to cancel out. The simplified version here is x squared minus x cubed plus c. Is that all right? Okay. Number 2. Number 2 doesn't quite look like the things that we've been doing. It doesn't look like any of the rules exactly, but it can be changed so that it does. How could I rewrite number 2 so that it would be more helpful to use the properties I have? Yeah, instead of writing it as 1 over x to the 6th, I can bring the x to the 6th up into the numerator. That's a property of exponents. And I can write it as x to the negative 6. Okay, so the x to the negative 6th, I'm going to increase the power by 1. What do I get if I increase negative 6 by 1? Negative 5. Be careful, because sometimes we get going quick and we inadvertently forget that we're working with negatives, and this one's negative, so it goes to negative 5. I divide by the new power, negative 5. Anytime I have a constant, like this one, a 2, all I have to do when I take the antiderivative is simply attach an x to it, right? because how do I do it when I take a derivative? Well, I remove an x. If there's an x present, I remove it. If there's not one there, I attach it. So this is minus 2x. And then what? Plus c. Again, gateway stuff, we stop here. But if we're looking at this from the perspective of a problem that we're turning in written-wise, this doesn't look like the form in which it began. If it had began with x to the negative 6, I would have no problem with you leaving it as x to the negative 5, but it didn't start that way. It started with a positive exponent in the denominator, right? So we're going to return it back to the denominator from whence it came, right, and make it back into a positive number. So I've got 1 on top now. The negative 5 is still in the denominator, and now I have an x to the 5 in the denominator as well. And the other pieces all remain the same. Is that okay? Okay. Square roots. We always kind of throw them in there, right? It's not as ugly as it kind of looks. It kind of looks pretty ugly right now. I've got both an x and a square root of x in the denominator. So if you'll remember, square roots have powers as well, like I can rewrite them in a power form. How can I write a square root instead of it being written as square root as a power? A power of 1/2. So this is x, and then it's x to the 1/2. So what do I really have when I have x times x to the 1/2? I'm going to do a couple steps in between. You may not need to see them all. That's okay. Yeah. X times x to the 1/2 is x to the 1 and x to the 1/2. And if I add a 1 and a 1/2 together, I get x to the 3/2. But the x to the 3/2 is still in the denominator at the moment, much like the x to the 6th was on this previous problem. So if I rewrite this again, I'm moving it up. I will have x to the negative 3/2. And do you have to show every single one of those steps to do this? No, just whatever you need to get to the ending part where you can actually begin to take the antiderivative is fine. Okay, does everybody see how we got there? That's the important part at this point. Okay, so what are we going to do? What rule am I going to use in order to take the antiderivative? The power rule. And the power rule says I do what? I add 1. So I have a negative 3/2. What is negative 3/2 plus 1? Yeah, negative 1/2. So this is x to the negative 1/2, and then plus c, right? On a gateway, we would leave it like that. We would leave it as x to the negative 1/2 plus c. But on our written work, how are we going to rewrite it? What is it? 1 over the square root of x plus c. We forgot one piece along the way. I was worrying about the radicals. What piece did I forget? Did anybody notice it? The dividing. Yeah, so over here, I need to divide by what? The negative 1/2, the new power. Okay, good. What is dividing by 1/2 equivalent to? Multiplying by 2. So instead of a 1 up here, I will actually have a 2. You can put the negative in front of the 2 or down at the bottom. It doesn't really matter where the negative goes. But dividing by 1/2 is the same as multiplying by 2 over 1. So I have a 2 that shows up. Sorry, I was so excited about my square roots to get that part done. Don't forget the number parts either. Okay, is that all right on 3? How does number 4 sort of create, memories of other things we've done? What about it looks different than the previous 3 problems? What's that? It looks like there's a product, right? And there's a product, but we haven't had like a product rule written out for antiderivatives, correct? There's a very good reason for that. And the very good reason is it's really complicated to do product rules and do antiderivatives. In fact, pretty much all of what happens in chapter, I can't remember which one it is in your book, if it's 5 or if it's 6, but it's going to be talking about what happens when I have products. That's not Calc 1, it's Calc 2, so we don't have to do it, all right? So if I'm not going to do a product rule, what other option would I have on this problem? Multiply it out, right? It's algebra simplification. That is the only tool you're going to have. That's really nice because it means you don't have to decide. Do I do a product rule or do I multiply it out? Well, you don't have a product rule, so you multiply it out. Okay, so we're going to multiply out what we have here. Let's see, I have x times 3x, so that's 3x squared. In the middle, I have 3x, and in the outside, I have negative 2x, so that's positive x. And then my last term is minus 2. And notice I wrote a script s at the beginning, so the dx is still at the end every single time until I actually take my antiderivative. Kind of like with to-do limits, right? The limit doesn't go away until I actually plugged in the value for h or l or whatever, my x, whatever my variable was. All right. So what's the antiderivative of 3x squared? 3 comes along, now what? X to the third over 3. Okay, what about the antiderivative for x? Right, x squared over 2. There's an understood 1 power here, right? So x squared over 2. And then what about for negative 2?
Minus 2x.
Right, minus 2x. And plus c. We don't have very much to clean up. What's the only thing we can really do to clean it up? Yeah, divide out those 3's. So we can actually write this one as our solution x cubed plus x squared over 2, or you could write 1/2 x squared if you wish, minus 2x plus c. Is that all right? Okay, we're going to do a trig one. A couple of them, actually. All right, so the first piece, the 1, that's nothing to do with trig. What's the antiderivative of 1? X, okay? But how do I get cosecant x cotangent x? Yeah, its antiderivative is actually the cosecant. And the sign changes, right? Which, if this one's positive, this one's negative. Ours happens to be negative, which means what's going to happen? It's going to become positive. So this is positive cosecant of x. And then plus c. So the nice thing about the trig, typically speaking, at least on some of them, is that there's not any simplification at the end. If it's one of those exact rules, there's no simplification at the end. I say that, and then we're about to do one that's kind of messier looking, but is that one okay, the one which said? We saw cosecant, cotangent. It's one of those specific rules that we have. We just apply it and we move on. All right, so this next one is not a specific rule that we have. It's kind of ugly looking. And this is one of those places where having that list of identity rules, especially if the trig is a little rusty, or maybe it's a class that you did in a pre-calc format and didn't focus a lot on the trig or something like that, it might be helpful to have those properties present for you. So the pre-calc, or the trig properties that talk about this particular denominator tell you that there's a way that you can rewrite it more simply that doesn't involve subtraction. Does anybody remember what 1 minus sine squared is? It's cosine squared. So the rule itself is a Pythagorean identity, and it looks something like this. It says that the sine squared of x plus the cosine squared of x equals 1. And if you were to subtract the sine squared to the other side, that's exactly my denominator. Do you guys see that? So I can rewrite this denominator as cosine squared of x. Now, that is way better. The fact that there's not addition and subtraction in the denominator whenever you're doing algebra components or when you're doing trig components is a preferable option because it allows you to break things apart from the numerator. And you can't do that if there's addition and subtraction in the denominator very well. So what can I do now? Well, you see a sine and you see a denominator that's a cosine, and there's another trig property that talks about what sine over cosine is. What is sine over cosine? It's tangent. Now, I don't have sine over cosine, I have sine over cosine squared, right? But I could split it up so that I do. So I can rewrite this instead as the sine of x over the cosine of x, and then I have 1 over the cosine of x as the other piece. So sine over cosine is now tangent, as we said. But what is 1 over cosine? It's secant. Again, these are all three of the properties, types of properties on that trig identity sheet. The first one's Pythagorean, the second one is a quotient identity, and the third one is a reciprocal identity. Those are the only three that I'm asking you to know, is those three types. So all three of those are present on that paper. So now I have tangent of x and I have secant of x. And that's a very good place to be because that's one of those properties, right? What's the antiderivative of tangent x, secant x? Secant x, right? It's this one right here. I know that the secant and tangent are written in reverse. That's irrelevant, right? They're commutative, so that's fine. So over here at this point, this is just secant of x. Somebody say it. Thank you, plus c, plus c. Yeah, secant of x plus c. Okay, all good? Okay, we're going to change the direction slightly. Everything we've done so far are the things that are showing up on your derivative gate, your antiderivative gateway, okay, in about a week, okay? A week from Friday. What we're going to do next is going to be able to find actually the c value, okay? So if I know that I've got the plus c, and I've got this, this graph that can shift up and down, and they give me 1 point on the graph, then all of a sudden it fixes the graph, and I can't do any more shifting because I was given a point that has to lie on my graph. Okay? So that's what's going on here. The question actually starts out, and interestingly enough, it has the notation f prime. So as I take the antiderivative here, I won't turn it into capital F because it was given to me as f prime. So notationally, I can simply remove the prime, and I am doing its antiderivative. Does that make sense? If the prime's there and I can remove it, I don't have to be capitalizing. So we are taking the antiderivative of 4x squared. What's the antiderivative of 4x squared? 4x cubed over 3. Let's see. Okay, all good? Now here's the cool thing. They tell us at the end a point. They tell us when x is equal to -1, y is 3. Or f of x is 3. So I can plug those in. I have 3 over here. And then I have the 4 and the 3 that are here, but my x is -1. So I have -1 cubed plus c. And the only thing I don't know now is c, so I can find it. All right, so what is -1 cubed? -1 times 4? -4, and so I have -4 over 3. I have 3 on the other side, so what will I do? Add my 4/3, and we'll keep it exact. So what is 3 plus 4/3? Yeah, it's 13 over 3. It's a little bit of fraction addition for you. It's a throwback, right? The answer is not 13 over 3 equals c. The answer to the question is the actual function that we've created. So I come back up to this function. So f of x equals 4x cubed over 3. And then it's plus the value that I just got for c, 13 over 3. So in this final answer, there is no plus c because I found it. Okay? Make sense? Let's try another one, same directions, except that there's an extension of an idea. This one says f double prime of x equals x squared. And I'm still supposed to recover, that's the word they often use, recover the original f of x function. So I'm going to have to do this in 2 steps. If I take the antiderivative of f double prime, what will I get? I don't mean the function, I mean the name of it. What will the name be? F prime, right? I'm removing one of the primes. What is the antiderivative of x squared? X cubed over 3 plus c. And I'm going to have another c in a moment, so I'm going to call it c1. because I'm going to have another c. Now at this point, I actually have some information that allows me to find the c. Because I'm told that f prime of 0 is 8. And I have a function now that says f prime of x is all this stuff. So I should be able to use this just like I used the information back here for f to find out what the first, that is my c1, value is. So this one says that if I let f prime equal 8 and x equal 0, I can find c1. And what is c1? It's just 8. So it doesn't have to be the value that's given, right? F prime of 0 equals 8, but it happened to be here just because of the function I was using and how that plugged in, right? So at this point now, I'm going to take the same function I created and I'm going to put the c1 value in. I now have x cubed over 3 plus 8, not plus c1, plus 8. Okay, that's step one. If I was just asked to find f prime, I'd be done. But I want to find or recover f, so I just do it again. What's the antiderivative? So now I'm actually at f of x cubed over 3. Close. X to the fourth is right. Over 12. Why 12, Caleb? Yeah, so I need to divide by the 4. That's what you had said, Adeline. And then this one right here already had a 3, so the 4 times the 3 would give me the 12. Does everybody see where the 12 is coming from? Okay, good. And then what about the 8s? 8x. And then plus c, right. And I'll call it c or c2, something different than I called it before. I called my first one c1, so we'll call it c2. But I'm not done. I'm supposed to be able to find that c2 value. And I can do that using the second piece of information up here. F of 0 is 4. So this is 4 is equal, it's 0 to the 4th over 12 plus 8 times 0 plus c2. What's c2? Yeah, it happens to be the same 4. Plugging in zeros when you're having algebraic, right, like polynomials and so forth, there's usually very nice. So we end up with a function. What? What is our answer to this question? That's it. X to the 4th over 12 plus 8x plus 4. Any questions on those? Okay, so those last two are not going to be gateway stuff. But they are additional pieces of information that we're going to be working with as we do homework and quizzes and things like that. Any questions? All righty.